Hello, everybody, and welcome to the last plenary session. This is really a nice advantage of the online system that immediately everybody is there. And it's not like usually, could you please stop talking in the background and could you shut the doors and let's start in a minute. And it's my great pleasure to chair this last keynote session of the conference. And first, I would like to take the opportunity to briefly thank our hosts, even if this is maybe not the appropriate moment. But I know that Megan and Melissa, you never meant to organize an online conference here in addition to the physical one, which is still ahead of you. And I think from my perspective, it was a great success. And despite some natural limitations of the format and like technical things in the beginning, I think the platform allowed a lot of informal interaction, and I'm really excited and inspired after these 3 days. So I have a lot of chances to catch up with people, but also to see a lot of interesting signs. And I also felt how this was lacking over the past 2 years. So thanks a lot for this. Also to your team, of course, because I know it's always on many shoulders. And in particular, I'm also excited about the keynote. So I think you picked really up-to-date and highly relevant topics. And the last one will be on urban climate informatics, an emerging direction in urban climate research. And urban climate informatics is a evolving research field that takes advantage of different technological trends, which can be capitalized on, including advances in sensors, in digital infrastructure, so new data, but also new data sources, but also new algorithms. But also in a bit wider view, it is related to maybe a paradigm shift in urban climate analysis, changing how we do science and expanding the research questions in the field. And I've seen a lot of interesting studies on this today. So I already got a guess of the uptake in the community, and then this is really getting some momentum, and therefore I'm really looking forward to the speeches today. And I think you found the perfect speeches, the perfect speakers for the topic. The first one, Ariane Middel, has been conceptually developing the field and the idea. And the second speaker, Zhonghua Zheng, is on the forefront of actually using AI and machine learning in urban climatology. So I would quickly like to introduce the first speaker. We're going both talks in a row. And then afterwards, we'll have time for a Q&A session. For the Q&A session, as before, I would like to ask you to use the Q&A tab on the right-hand side. So there's a general chat, but there's a specific Q&A tab which allows to put in questions either with your name or anonymously, and you can also rate on questions of others, which is a big advantage. So take a chance, the opportunity to ask questions, or also to vote for questions you consider important. So the first speaker is Ariane Middel, and she's an assistant professor in the School of Art, Media and Engineering and in the School of Computing Augmented Intelligence at Arizona State University in the US. And she received her PhD in computer science from the University of Kaiserslautern in Germany, and her first master degree from the University of Bonn in Germany also. And Ariane's research focuses on climate-sensitive urban form design landscapes and infrastructures in the face of extreme heat, and also in climatic uncertainty. And amongst others, she directs the Shade Lab, and she's a recipient of an NSF Career Award on human thermal exposures in city. And also she's a newly elected president of this association, and also active in the board of the AMS built environment. So I'm really looking forward to your talk and overview on this exciting new field, and the screen is yours, Ari.
Thank you so much, Benjamin, for the introduction. Let me see if I can actually, well, before I share my screen here, share screen. Okay, so here we go. Thank you so much for the introduction, Benjamin. It's really an honor to be here today and to talk about these exciting new developments in the field of urban climate, which we call urban climate informatics. We are all here today because we have a passion for urban climate, and our field is really becoming more and more important than ever. We have still rapid ongoing urbanization that's combined with climate change threats that threaten urban livability. There's urban overheating, urban heat islands, intra-urban heat. We have extreme weather events, flooding. Think of Pakistan that happened earlier this week. Hazardous air quality, increased energy consumption. So there are a lot of problems that add on to the climate change issue. And all of these things have really widespread health, socioeconomic, and ecological impacts. To tackle these challenges, numerous subfields have been developed in the field of urban climatology, and they have evolved over the last century to essentially document, examine, and also model urban climate at various scales. Some notable events in the early 17th century, the thermometer was invented. That was the first time where researchers actually could systematically record weather conditions across the globe. And then in 1851, there was the year when the very first weather map was generated from 22 weather stations that was displayed at the World Exhibition in London. And then fast forward 100 years, we have weather satellites. TIRWS was launched in 1960. We can now record surface temperatures at unprecedented resolution. And I really highly recommend a recent paper by Ian Stewart, who wonders why should urban heat island researchers study history. So it's a really great read. So if you have time, click on this link and read this paper. So despite all this progress that has happened over the past century, if you take micrometeorological theory and then try to apply it to urban areas, that is really still very difficult because the built environment is so heterogeneous and so complex. So conventional observation methods that we have often can't really provide fine scale resolution data temporally and spatially. So we need denser observation networks. We need novel data sources to answer a lot of the open questions. Also, in the past, the focus has really less been on human factors that lead to personal exposures to environmental stressors. And we really don't know who is exposed, when, and where, because we lack the mobility data. So now this is where urban climate informatics comes in. Urban climate informatics, or UCI, is an evolving research field that originates from two relatively established domains. The first one is urban climate. That's why we're all here. And we're concerned with the interactions between the city and the atmosphere. And then the second domain is climate informatics. So that's research that combines climate science with approaches from statistics, machine learning, and data mining. Climate informatics focuses more on the computational approaches in climate science, but then UCI, or Urban Climate Informatics, takes up a broader, very multidisciplinary approach. So my colleagues and I listed down on the slide right here recently guest edited a special issue on urban climate informatics and published a paper to coin this term. And we defined urban climate informatics as a domain that aims to explore and understand complex urban climate systems and human environment interaction. So it's not just about the city and the atmosphere, but humans are a big part of this, using new technological, methodological, and systems thinking approaches. So urban climate informatics embraces a more integrated and really a more human-centric method to address urban climate challenges that we experience. And this is enabled through novel sensing, really non-traditional data sets, crowdsourcing, big data, digital infrastructure, advanced analytics, artificial intelligence, and so on. So I'm going to show you a figure now on this next slide that details all the different advancements that have happened that contribute to this field of urban climate informatics. So urban climate informatics essentially takes advantage of 4 trends to answer contemporary climate challenges in cities. And those are listed in the corners here. So we have advances in sensors, improved digital infrastructure, novel data sources, and then leading edge analytical algorithms and platforms. So let's go over all of these 4 corners in more detail. So the top left, advances in sensors. Sensors become smaller and smaller in size. They consume less power, maybe run on a battery. They're more affordable. There are a lot of low-cost sensors you can purchase these days. And they're also improved methods of data transmission. So you could use Wi-Fi, you could use 5G. There's a technology called LoRaWAN. So that's really easy to get the data off of your sensor onto your computer to do the analysis, and you don't need any wires. The sensors nowadays are also location aware. That means they are GPS enabled. They know where things are being sensed. There's this new technology of Internet of Things. I'll talk about this in a little while when I give you an example. And all of these technologies really allow you to do a more real-time data collection than previously recording the data on a data logger, going back to the lab, downloading the data. So there's this real-time aspect that's really helpful. Then the second box to the lower left, in addition to the sensors or data from sensors that we traditionally used, we now have environmental data that are collected using new data sets. So those include 3-dimensional building data, data that's generated by the community, crowdsourced data, social media data, data from Twitter, Facebook that can be scraped and used for analyses. And then we also have public domain data sets that are frequently used for analyses. So in addition to that, we also have a lot of commercial sensors. Think about smartwatches, wearables, or Fitbit, the Nest sensor that manages the heat or cooling in your home. And those sensors are really non-expert friendly. And citizen science data collection has really become mainstream using these sensors. They're now crowdsourced data collections that are supplementing the data that academics or researchers would collect using traditional sensors. So the third box, state-of-the-art analytical algorithms and computer systems. They have also greatly enhanced urban climate analytics. So we have technologies such as artificial intelligence and deep learning, and those computer science methods are more and more used in the urban climate community, for example, to describe the looks of the 3D built environment. There's a lot of research been done with street view images and other big data types, and I'll give you an example in a little bit. And then lastly, the last box, accessibility of digital infrastructure for storage, analytics, and communication of the results really have transformed various approaches. So now we have cloud computing, we have edge computing, we have Amazon Web Services, things are calculated in the cloud. So all of these 4 cornerstones of urban climate informatics really foster applications in this area and are really advancing the field of urban climate into a more human-centric field and approaches. So collectively, if you take all these advancements, the novel data sources, sensors, computing methods, they've really led to a paradigm shift, as Benjamin mentioned earlier, in urban climate analysis. And this shift has significantly changed how we do science or what we understand about the urban atmosphere as a result. So if you have your traditional urban climate science that focused on the city atmosphere interactions, but now there's really a trend to tackle challenges of the Anthropocene. That means climate change, urban overheating, all the challenges I listed on the first slide, air quality, climate injustice. And there's also a new trend towards comprehensive analyses of the dynamics of urban climate and the human-environment interactions at very fine scales, both temporally and spatially. So it's not just the city and the atmosphere in isolation. There is the human aspect that gets added into the analyses. There's also a shift from the traditional urban heat island definition, which is the difference between air temperatures in rural and urban environments, towards a more intra-urban hazard distribution and thermal exposure assessment, because it's really not that relevant how air temperature is in the rural environment versus the city, if you're looking at how people are moving through the city and how they're exposed to these different hazards, especially heat. So it's a much more relevant metric to look at intra-urban distribution than to compare to a rural station. There's also a trend to lower cost tools and data that were actually acquired not necessarily for urban climate purposes. And that goes back to the Street View data, for example. Google did not generate Street View data for our community to use, but it's a really great resource and a lot of people have used it for many applications. Also, the field of urban climate informatics, similar to the field of urban climate, is actually highly interdisciplinary. So we have architects, engineers, urban planners, computer scientists, even local government representatives. So having this diverse group of experts solve urban climate problems really allows for a more complex and also solutions-oriented analysis, going from health sciences to social justice and equity. So there's a highly interdisciplinary approach when it comes to urban climate informatics. And then lastly, research results are now communicated to non-experts. It's not just distributed among us as a community, but also to the broader public, using new platforms, new visualizations. People generate websites. There's social media, dashboards to monitor certain conditions. So this maximizes the broader societal impact that our work has. So let me give you some examples of urban climate informatics studies. So this is a very early example from 2018 from my lab, where we used Street View images to describe urban form. And as I said, Street View images have been really popular recently to answer science questions. They have been used to analyze walkability and bikeability of neighborhoods, look at how accessible bus stops are, traffic safety, obesity, physical activity, but they've also been increasingly used to characterize the built environment. That means how many trees are on that street or next to the sidewalk, how many floors do these buildings have? Are there crosswalks or sidewalks in the streets? What's the age of buildings? What's the land use? And this particular study here was using Street View images to calculate the sky view factor, which is the amount of visible sky if you look up on a hemisphere. And it's an important factor for urban climate analyses because it's essentially a 2D version of describing 3D urban form. And what we did in this particular study is we scraped those Google Street View images, we projected them into hemispherical views, detected the sky using artificial intelligence, calculated the sky view factor, and then we were able to map the sky view factor on those streets in various cities. We've collected a total of 70 different cities, and that allows us to compare the form or the built environment of these different cities using these sky view factor footprints. I would like to point out another approach that's hot off the press. It was published 3 days ago by Matthias, I'm butchering your name, I'm sorry, de Musere. It is the very first global map of local climate zones. It's at 100-meter resolution. It's an example for processing data in Google Earth Engine and using machine learning. And I highly recommend this data set. So if you get a chance, check out the paper and download the data for you. It's free to use for your research. And then the last example I would like to give is an IoT, Internet of Things approach that we're currently working in my lab. It's called Martini. A Martini is a low-cost sensor that measures MRT, but it's a small sensor, so it's not MARDI, which would be a large sensor. You can see MARDI on the screen to the right here, but it's a tiny version of MARDI, so that's why we called it Martini. It's a box that has a Raspberry Pi in it. It measures air temperature, humidity, wind speed, and UV radiation. But it also has a globe thermometer that can be used to calculate mean radiant temperature. And then there is a webcam in that box that faces towards a certain area that you choose it to face to. And we would like to deploy this box in a park in Tempe to monitor how people use this park as the weather changes. So the camera takes videos, it transports frames from these videos, uploads them to AWS, to the cloud. There's an AI on this server that does the people detection. It also detects if people are walking in the shade or in the sun. And again, we'll be deploying this IoT device in a park close to a playground to see how space use changes with air temperature and hopefully help the city make decisions on where to implement shade structures in those parks. This is just one paper that was published in a special issue on urban climate informatics that I mentioned earlier with my colleagues Benjamin Bechtel, Matthias de Muser, and Negan Nazarian. I highly recommend checking out the special issue. It just closed. The link is over here, and it has various more examples on local climate zones, on smartphones, using wearables to collect data, IoT-based approaches, novel sensing using rotating panorama cameras, crowdsourcing applications, and so on. So now, in conclusion, urban climate informatics is a newly evolving field. We just coined this term in 2019 in a keynote at EGU, and now with the special issue. UCI embraces various scientific disciplines. So there's anything present from data science, geospatial analyses, urban design, health, policy, planning, computer science, and so on. And there's a clear paradigm shift, as I mentioned before, that can be seen from focusing on the city atmosphere interactions alone to actually tackling grand challenges of the Anthropocene, which would be climate change, urban overheating, poor air quality, climate injustice, and so on. So these new advancements that you saw on the overview figure offer really unprecedented opportunities for us to understand these grave problems and to support a variety of application. Urban climate informatics also pushes the boundaries of our observational networks. So we have denser networks using low-cost sensors. Our models can become higher resolution. We can increase domain sizes with more computational power, computations in the cloud. And this really will help us to predict or to estimate hazard distributions in cities at unprecedented details. There's also high resolution 3D city data that will allow us to answer questions on things like, where do I plant trees for optimal placement? What's the amount of available shade, and so on. And digital twins are really on the rise as well. So these are replicas of cities where you can do calculations of atmospheric phenomena. And so all of these trends, urban climate informatics, will really undoubtedly shape the urban climate research agenda for upcoming decades and really positively impact fundamental applied and policy relevant research. So is the future of urban climate in the cloud? We will hopefully find out at IAUC 11 in Sydney next year. And with that, I would like to close. Thank you for your attention. And the Q&A session will follow after the next keynote speaker. Thank you.
Thanks very much for this great overview and framing of the field. And I think many people around here are already contributing to the new field without maybe even knowing the conceptual background. So I also recommend reading the paper, and I've seen, as I highlighted before, I've seen a lot of exciting stuff today, which really pulls into the same direction. And yeah, even if the future of the field may be in the cloud, the future of us as a community maybe is not only online, hopefully, and therefore it was a very good reference to Sydney in the end. Well, now we come from the overview to some pioneering work in the field, and our next speaker is Zhonghua Zheng, who is now at the University of Manchester, and before was a postdoctoral postdoc fellow at National Center for Atmospheric Research, NCAR, and his research interests include environmental data science, urban climate and environment, and air quality and aerosol properties. He got his PhD in environmental engineering and civil engineering from the University of Illinois. And yeah, he worked also at Bayer and at the Oak Ridge Laboratory. And yeah, as I said before, he's a pioneer in combining Earth system models, so large-scale modeling data with high-resolution simulations using machine learning and artificial intelligence. And I'm very much looking forward to your talk, and the stage is yours.
Thank you, Professor Bechtel. Let me share my screen. Okay, can you see my screen? Okay, so
looks all fine.
Okay.
Yes,
good morning.
We can see it.
Great, nice. Good morning, good afternoon, and good evening, everyone. My name is Zhonghua Zheng. I just started my new role as assistant professor or UK lecturer in data science and environmental analytics at the University of Manchester this week. And before that, I was an advanced study program postdoc fellow at National Center for Atmospheric Research or NCAR in the United States. It's really my great honor to present my work or our work, and Professor Middel just gave us a very broad overview and a solid foundation of the urban climate informatics. And today I'm gonna dive into a specific concrete example. So broadly speaking, I'm interested in coupling data science and numerical simulations to empower atmospheric and environmental research with a focus on urban climate research. And today I'm gonna present one of the applications of urban climate informatics, which is about how to use machine learning to project urban heat waves at a global scale. Oops, get stuck. Okay. Usually I would ask the audience a question: why do we study urban? However, given the nature of this conference, this kind of question is redundant. On the other hand, global warming is causing many problems, such as heat waves. And in the last few years, or just in the last couple months, we have already witnessed several heat wave events over the world, like United States, Japan, China, and the UK. When we combine two terms, urban and heat waves, together, now we have a new term, urban heat waves. However, projecting urban heat waves in the future is very challenging. The first challenge, comes from the urban representation. As we know, despite the fact that more than half of the world's population living in the urban areas, the area of urban only occupy a very small fraction of the globe, right? So for large-scale Earth system modeling, this tiny fraction could be ignored to some degree because the impacts on large scale are limited. So scientists didn't invest lots of efforts into developing urban representation for Earth system models. As a result, when people doing urban heatwave projections, especially, at a large scale, they just use a coarse gray cells, which could introduce bias. And I believe most of us have heard the term urban heat island, which means a difference in temperature between urban and its surrounding areas. Let's take a look at this simple example. Here we have gray cell average temperature. Basically, in each gray cell, we take the average as well as the urban temperature within the same gray cell. If we take the difference, we found urban specific temperature could be higher or lower than the gray cell temperature. As a result, using gray cell temperatures to study urban heat waves is not accurate. It's might be biased. The Community Earth System Model, CESM, is one of the few Earth system models that incorporates urban representation. Actually, I just used a simulation from CESM to demonstrate the difference between gray cell temperature and urban temperature in previous slide. Additionally, CESM developed by NCAR has a large ensemble, and this is a big deal, and I will tell you why. Just keep in mind, CSM large ensemble has multi-members, and the difference among members is a very tiny initial condition in air temperature. Another challenge comes from the multi-model projections. Because each model has its pros and cons, and we have to combine the prediction of each model to get robust results, such as the ensemble forecasting model for COVID-19 developed in early 2020. So the advantage is that multi-model approach provides not only the mean value, the average value, but also the uncertainty, and this is very important. There are two sources of uncertainties generally in Earth system simulations. The first one, we call it internal variability, which comes from natural processes. And we can adjust this uncertainty by rerunning the same model many, many times with a very small difference in the initial condition. And these simulations are referred as multi-member ensemble. Now we know the butterfly effect, right? A small change in the initial condition can result in large difference in a later state. So that's why I say CSM large ensemble is a big deal, because we can use them to quantify the internal variability of urban climate, and they are publicly available. Another uncertainty source is model parameter and structural uncertainty. So this type of uncertainty comes from model design. As we just introduced in the last slide, it can be adjusted by running many Earth system models, let's say CMIP, multi-model. For those of you who are not familiar with CMIP, it's a coupled model intercomparison project. So basically, different research institutions develop and run their own Earth system models following the same guidance and then submit their results for comparison. But we already learned from the first challenge, there is no urban representation in most of the Earth system models. As a result, we are unable to adjust the model parameter and the structural uncertainties. Within the urban representation, the urban temperature is derived using PDE, using partial differential equation from a set of physical variables. Then you may wonder, why not building the urban representation for each Earth system model? This is like a reasonable solution, right? I can tell you this is infeasible because each Earth system model has its own structure. It's not like we are buying a new desk to our office. It's more like we are remodeling our house. So when we are doing the remodeling work, it is possible that we are going to change everything, right? Therefore, what should we do? The solution is machine learning. More precisely, we call it supervised learning. because we want to teach machine learning algorithm to learn or build an emulator from CSM large ensemble data. And this emulator is a predictive model which describes the relationship between urban temperature and the physical variables. We will then use the physical variables from CMIP multi-model data as the input. Because now we have the input data, we train a machine learning model. The output will be urban daily maximum temperature of like the 2-meter temperature. That will be used for urban heat wave projections. With the urban daily maximum temperature, now we can define heat wave as 3 or more consecutive days with daily maximum temperature higher than 98 percentile. We use the data from 2006 to 2015 as a baseline, and this is used for each urban grid cell. Then we can get the urban heat waves in the present. Right? I use 2006 2050 as a present. And then also for the future, 2061 to 2070. However, we are interested in the difference or trend. So we calculate the difference between these two time periods. Then we repeat the same process for 17 CMIP models that we download data and then we apply this workflow. So with our machine learning workflow, now all the 17 CMIP models have the urban temperature and urban heat waves. And with the CMIP multi-model projection and the CSM multi-member large ensemble, we can quantify, we can study the uncertainty from different sources, and we can project urban heat waves. Let's begin our CMIP multi-model results for urban areas. I compare the future and the present urban heat waves in terms of intensity, frequency, duration, and the total days. And we discovered that future urban heat waves will be more intense, more frequent, and longer lasting. As you can see, even the blue color from the color bar, you can see the blue color remain mostly also positive. So that means it's like we will face more intense, more frequent, and longer lasting urban heat waves in the future. Additionally, I want to emphasize that I use a signal to noise ratio to identify regions where models agree with each other, because this is important for this kind of large scale studies. And I label them using the black dots. But for this presentation, it's challenging to show these regions, and you are welcome to read our paper for more information. Next step, I use the trend of urban heat waves to minus the trend of non-urban heat waves to quantify the bias, to highlight the importance of using the urban temperature. And we found that grid cell temperature, that means we use grid cell temperature, people used to use this to represent the urban, it almost underestimates the trend in urban heat waves in terms of intensity, frequency, duration, and total days. As a result, it emphasized the importance of using urban temperature rather than the grid cell temperature to model urban heat waves. Everybody here might have heard of a black swan event, which is a highly unpredictable event that has severe consequences. The term gray swan is derived from the black swan. Here we define urban heat wave gray swan event as heat extremes that cities will face in the future. And you know, these events are virtually unpredictable based on historical observations or existing models, such as CSM large ensemble, because we can run CSM model many times. Somehow it cannot capture this kind of pattern. However, they can be better predicted by using our multi-model approach. And here, based on our previous results, we just select 4 regions based on their intensity. And let's take a look at the one in North China. Let's consider trend of intensity And this figure shows a probability density function, or the PDF, for all the urban gray cells in North China. The dark blue denotes every single member from CSM, and the dark red denotes every single model from CMIP. And the dashed line denote mean value across all the urban gray cells. And we also have the mean and the confidential interval of the density. And from the statistics, we know that area under the curve of the PDF is the probability, right? So let's assume an event is unlikely to happen based on CSM. Let's say under the blue curve, we find a point where the area under the curve is about 0.01%, okay? And we can find the corresponding x-axis, let's assume it's here. However, based on the same x value, if we consider the area under the red curve, the area will be about 15%. This is huge difference, right? Compare like 0.01% to 15%. Therefore, when we project future climate-driven risks in urban areas, we need to consider multi-model to ensure the robustness. In summary, we developed a nonlinear urban climate emulator to estimate urban temperature and enable the urban heat waves projections at a global scale. Then we adjust the trend of urban heat waves in the future, as well as the importance of using multi-model robust projections. And this is an example of the application of urban climate informatics. And currently, I'm working on improve this kind of emulator and also make the data available for public. Then everybody can use cloud computing to access the data, and those are free. Okay, I would like to take this opportunity to thank all the co-authors for their contributions, and thank you very much for your time. I'm happy to take any questions.
Thanks very much for this very nice presentation. And maybe Ari, could you also come back to stage? So I would like to encourage everybody again to ask questions in the Q&A panel. So currently we just have one question, which is for Ariane from Chandana. She wants to know what martini costs.
Oh, martini is a little bit more expensive than your average martini drink. So the Raspberry Pi, I think, is about $30 or so. Then all the sensors attached to the martini are in the range of $5 to $10. The wind sensor was actually really expensive. It was $50. That's the most expensive piece in this whole setup. And I would guess with including a battery and solar panel. So we're actually currently trying to make it independent of power supply because it's not very convenient to have a power, like an extension cord, go through the whole park to the martini. We are looking at $200, I would say, roughly. And that is in comparison to the research grade high accuracy MARDI setup, which runs at around currently $22,000.
And do you have any first results from it? So can you
from the martini?
The data quality already?
So we did deploy a martini in a park last fall, but we had this power supply issue. And so we collected data for 2 days and compared the data to MARDI. And of course, it's lower accuracy data, but there's a publication by my colleague Jennifer Vanos et al. That developed correction factors for the gray globe, specifically the setup that we used. So that correction factor is actually quite correct. So we have these two days of preliminary data, and we just solved the power supply issue. So hopefully we're waiting for the email of the city that says, yes, you're good to go, you can deploy, because we have to, there are some legal issues with doing research on city property. So as soon as we have the go from the city, the Martini will go up in the park, hopefully next week.
So then we have a new question for Zhonghua from Gerald. Can you evaluate your model using current heat wave events in city? And that is running the model for the last 30 years or so.
Yeah, this is very good question. So I forgot to mention the scenario that we are using. So for the talk that I just present, I use the RCP 8.5 scenario. So it's kind of like the high emission scenario. So I believe like if we compare different like emission scenario or different SSP, then we can better quantify and validate our prediction. So, yeah, so that is like our next step.
Thanks. So I was also wondering about the emission scenario. So I have this question here on my my personal list. But now there are more questions coming in, which is great. So there's another one on Martini. And the question is, what are the parameters that are being measured and how is the data transferred? So maybe you could also tell us a bit about the back end, because that's, I think, something various groups are facing, which are currently developing some sort of microclimate networks. And then the question is data transfer, but also what type of database, how do we store and process them in the back end?
Yes. So the first version that we had developed last year was needed to essentially log onto a Wi-Fi network, which was not very convenient because there was no Wi-Fi in the park available. So we had a student actually create a hotspot with his phone, and it was not very feasible and scalable. So now we generate our own hotspot, and we use which works well for the US. I don't know if that is available in other countries, but Google has a plan, Google Fi. You can get unlimited data, an unlimited number of SIM cards for $70 a month. So we create our own hotspot using the Google Fi SIM card, and then the data that's being collected by the device is, so we're doing this on the edge. So the data are streamed to an AWS server, and then all the processing happens on the AWS server. So it happens in the cloud. Initially, our first version of the device had a Nano Jetson, which is a small GPU. It's about $100, and the people detection was actually done in the box on the small GPU, but it was overheating, and we wanted to have something that's scalable. So we decided to move that process over to the AWS server.
Thanks. So then there's another question on digital twins, which is considered catchy buzzword, which probably is true, as you said. I mean, it catches a lot of attention, but then also that means that everybody tries to see how they can hook in and like maybe promote their own interests in that new field. And the question is, what role could they have in urban climate analysis?
I think the trend is generally really going towards digital twins, but I think we're still a little bit off from like feasibly using them. I think a lot of groups are working on their versions of a digital twin. I think there's a lot of standardization that needs to happen in this field. Also, a true digital twin would allow you to in real time run simulations, do computational steering, meaning that you can change parameters in the digital twin and will automatically adjust and give you different results. And the amount of accuracy you can implement in such a digital twin is like really bottomless, right? Because the more accurate you represent your city, the better results you get. It's the same issue with microclimate models. So I think it's the trend is generally good, but I think we're not there yet to have a true digital twin. So hopefully in the next 5 to 10 years or so, we'll see some presentations on digital twins that are actually really fully functional.
So maybe there the AI part comes in. If you want to have it, just click on a button, and then probably you cannot run a very huge LES model in the background. So is that also a way for plugging in this analysis in digital twin projects existing?
Yes, I think as we move forward in time, I think more and more people will try to not actually model the physical processes using equations, but actually trying to have an AI learn from large amounts of data that represent these physical processes to then use this intelligence to estimate other parameters that you would otherwise calculate using physics and equations. Yeah, that is definitely, I think, also a new trend that is going to be really interesting to monitor and watch what's going to happen.
So Zhonghua, there's another question for you, specifically about heat wave in tropical cities. So the question is whether you have more information on this, and yeah, it's from Vladimir, and he says that he lives in northeast Brazil, and there are no studies available currently.
Yeah, so let me share the screen. So this, you can see this is my results based on the RCP 8.5 emission data. And it's actually, you can see for the intensity, like most of them is like increase, but it's not like significant for compared to other regions. But I also, you can see the frequency, duration, the total days seems horrible, right? It's like all of them are red. I want to say this really depends on how we define heat waves and also the definition of heat waves. And also, let's consider a case. We have like, because we have the baseline for heat wave comparison, we compare future to present. So if the minimal temperature in the future is higher than the highest temperature at the present, then every day can be considered as heat wave event, right? So it really depends on how we define heat waves and also how the emission scenario, what the emission scenarios that we select. So I think there's no like the determined conclusion, but I think we need more experiments to test and to validate.
Thank you. Ari, are you still there? So Gerald is asking how the informatics or climate informatics could be used for indoor climates, which can be considered as part of the urban canopy, the enclosed part.
Indoor climates. Well, I think I mentioned before that nowadays we have technologies such as Nest sensors who learn about your AC preferences and use, and then automatically set the thermostat settings for your house. So that is a urban climate informatics approach if we were to take this information to optimize energy use in buildings, for example, to optimize indoor climates. That is just one example. Is that what you're getting at, Gerald, in terms of UCI and indoor?
I can also
can't respond, so sorry.
I can also add a comment. So I think now another topic of machine learning, because machine learning can be divided into three categories. We have supervised learning, we have unsupervised learning, and then we have reinforcement learning. So reinforcement learning is like not get that many attentions, but it's a very useful tool for optimization and also for different applications. And it has started being used for the indoor kind of climate control. So it's also, I think it's also a powerful tool in the future.
So Gerald again specified, and he said the question was whether you can actually get these data. And I think this refers to a wider challenge in the field, which is related to data ownership and privacy, and also discussed in the paper. But I would also like to give the floor to some other questions. So one is, as urban climatologists, what type of training do we need if we want to go into the field of urban climate informatics. So if you don't have a computer science background, can we do it? How can we contribute?
Yes, I think that is the beauty of the urban climate community too, which is, you know, the base community, is that it is largely interdisciplinary. So you may not need a computer science background, but maybe you have a colleague who's a computer scientist, and then you can work together. You bring the urban climate expertise, and then your colleague can fill in the machine learning, computer science, whatever aspects are needed. So it's a very inclusive community, and we embrace diversity, and I think you don't necessarily need to have this expertise yourself to be successful in this area. You find other experts that complement your knowledge. If you're and then as you work with that computer science colleague, for example, you will automatically pick up some knowledge in that field. And I think that is a way to, you know, slowly moving into that field, working with other people who have expertise in that area, and then you learn from them as you go as well.
So then there's another question again about how this can help to learn about indoor climates and indoor-outdoor relations from Negin. Maybe if I may, I would just add one small point on this. How do we get the data? So I think, I mean, it's really difficult to get a hand on all these indoor heating device data, but maybe some of them can be also captured accidentally. For instance, in the NetAtmo network, in the quality control, one of the most important processing steps is usually erasing the indoor data, because people put the outdoor station somewhere in another room, so they don't use it the way it's supposed to. And of course, you can turn it around. So usually you want to filter these data, but you could also take these data and capture indoor climate information actually this way. And there's been a really nice paper from the Berlin crew, so Daniel Fenner and others, who use this for some building energy model evaluation or parametrization. So that can be done, but that's accidental data, so that's not the big volume. So Ariane, do you want to give a final comment on that? Because there seems to be a lot of interest in the indoor climates and indoor-outdoor relations.
Yeah, I like this idea of flipping, you know, putting outdoor sensors indoors. There's also, and I think that was Negan's question about indoor-outdoor, as opposed to using stationary sensors, you could use people as sensors and have, you know, equip people with air temperature measurement devices, sensors, and then see where they are actually exposed indoors and outdoors, and see how that exposure changes throughout the day with, you know, different behaviors. So as opposed to tracking the space, you actually track people moving through that space and track the conditions, you know, along their routes.
Yeah. So there's a lot of new challenges, and there are also a few more questions regarding the accuracy and cost relationship, and then also data ownership. But we also slowly have to wrap up the session. So maybe I would give you both the opportunity for a final statement, and you can either comment on this or just wrap it up. So maybe Zhonghua, you can start.
Okay. So I think regarding the question about the training of data science and data mining, I think one of the goal for computer science people, they want to make it feasible, like easy access to everybody. So-called now we have so-called automated machine learning, and this is a pathway to achieve this. So that means we don't necessarily have very like the solid domain knowledge about machine learning, but we can regard this as a tool, and this can be very helpful for like the most of the domain scientists. And also this also requires the collaboration between domain scientists and computer science people to tailor it, to customize this for the broader community. So I think this is also so this is direct one of the future direction, I can say. And also from our side, we want to apply the machine learning and to make it try to improve the the model simulation, like to make the model faster, more accurate. And because computer science people, they don't have such domain knowledge, and we also need a collaboration between them. So I really highlight the interdisciplinary study. So by the interdisciplinary study, we can have more fruitful results, more fruitful products. Yeah.
Yeah, I totally agree, and I think that's also something Ariane highlighted, that it's an interdisciplinary field from the beginning. So, your final statement.
I think that was an excellent closing statement. Thank you all for participating in this session. It was a wonderful session. It was great to see you all, even if it was not in person. And stick around for the final session that comes up right after we close here, which is the handover from old to new executive.
Yeah, so that leaves me to thank you again, both speakers, and also everybody participating in the discussion. So I also like the session a lot, and then I would like to hand over back to the host of the conference for the closing.